So hello everyone, and welcome to this new webinar in which we are going to talk about FaMIVE, Failure Mechanisms, Identification and Vulnerability Evaluation. This is the first of two day seminars that we are going to have. Today we are going to talk about the FaMIVE platform. That is a tool to conduct performance-based seismic risk assessment of historic buildings in urban centers. Today, our guest speakers will be Professor Dina Dayala and Professor Ariana Guardiola. And tomorrow, we are going to have the second session in which we are going to talk about the seismic risk assessment for urban heritage in Valencia, in which Ariana will give us this specific talk. Then we are going to talk about the probabilistic fiber-based macro element analysis for global seismic response and fragility assessment in historic masonry buildings by Professor Fulvio Parisi. And then we will have Valentina Buonocunto in the next talk, that is integral in-plane, out-of-plane fragility curves of historic masonry buildings, implications on regional seismic assessment. And finally, we will end with our colleagues from Universidad Católica de Chile with a talk that is titled "A New Procedure to Derive Typological Fragility Curves for Unreinforced Masonry Structures" in an application of the Chilean case, in which we will have Professor Juan Carlos de la Llera and Chiara Palazzi and Juan Pablo Muñoz giving this talk. So today, our speakers will be Professor Dina and Professor Ariana. They don't need much introduction. As you all know, Dina is the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering here at UCL. She is full professor of structural engineering in the Department of Civil, Environmental and Geomatic Engineering. She also is co-director of the Epicenter, and she was the one that developed initially the FaMIVE procedure, and she has been working on it during the past 20 years. We also have Professor Ariana Guardiola from Universidad de Valencia, Politécnica de Valencia. She has been working on built structures to preserve them to posterity, and she has been also an invite professor here at UCL during the past year. Ariana has been leading the development of the new FaMIVE shell. She will speak about this in some minutes. Just before we give the word to Dina and Ariana, we just want to comment about the upcoming webinars and courses. Today we are having the FaMIVE, and in June we have scheduled a talk that will be given by Miyamoto International, in which Adriana Navarro and David Hodgkin will speak about vernacular construction for resilience and response. And then in September, we will follow with one of our Mediate webinars, in which we are going to talk about multi-hazard interaction, cascading impacts, and different indicators that will be given by the Mediate project personnel, in particular by Christopher White, Camila Lafranconi, and Marcelo Arosio. So without further ado, Dina, the floor is yours. Thank you all for connecting, and you are all very welcome.
Thank you very much, Rafael, for the introductions, and thank you all for attending this talk that we hope would be of interest. I will be trying to share the screen just now. Let me see. If I say share screen 2 for a minute, share, you will have to look up not much, but hopefully when I do this, you will be able to see my presentation. Thank you. So yes, so today we will be speaking about the failure mechanism identification and vulnerability evaluation procedures that we have developed at University of Bath and UCL in the past 20 years or so, shortly called FaMIVE or FaMIVE, depending on pronunciations. Today we are looking specifically at the seismic fragility assessments of masonry building, historic or more or less historic, but the emphasis is really on masonry buildings. And the importance is to determine seismic vulnerability assessment at the territorial scale on one end, but at the same time that this tool should be based on limit state analysis, based on performance displacement method, and applicable to diverse typology, so that on one end, we can compare the performance of masonry building with engineered structures, and at the other end, we can assess in a swiftly and efficient way large number of buildings using analytical procedures rather than empirical procedures. So what we will briefly, our talk will entail today, I will look a little bit at the urban dimensions of seismic vulnerability, look at what are the failure modes that we can highlight from past earthquakes. What does it mean, a safe configurations? Because ultimately we want to prevent this building from damaging and collapsing and affecting the population that lives and uses them. And therefore we need to identify, and as I said earlier, as we want to use and develop a tool that is as applicable as possible to the very wide range of masonry that covers our planet, then we also need to be capable of identifying typology and construction details in different contexts, which determine that structural behavior and eventually the safe configurations. Once we have identified that, we then need to collect these informations, and Professor Arianna Guardiola will explain us how we will now do this in a swiftly and, let's say, digital approach online with the new shell that we have produced. We will then look at how this data is quickly used by FaMIVE and how we can further analyze the output of FaMIVE to produce what we have already discussed in previous talk on these channels of webinars, the approach of determining capacity curves, damage thresholds, and deriving fragility functions for given typology. Before I progress any further, I would like to acknowledge and thank all my past collaborators and PhD students, which are now themselves academics, or working in the area of risk, of disaster risk and risk reductions. Dr. Elena Speranza, Dr. Sara Paraganoni, Dr. Viviana Novelli, Dr. Valentina Putrino, Ashima Kansal, Professor Attila Anza, Dr. Emre Kishali, and Dr. Pia Hannewold. And now we can deal into the, sorry. It's jumping up a bit. Yes, now we are on the right track. So as I mentioned earlier, the ultimate output is the definition of fragility functions. So how do we get there? In a very brief summary, through exposure characterization, which we need to do through direct data collections. We then use these direct data collections to determine what we call collapse mechanism and collapse load factor through the FaMIVE procedures. We, having defined the output of the FaMIVE procedures, we can identify buildings that behave in a similar way, so we can determine typologies. We can then simplify this typology to single degrees of freedom oscillators with a nonlinear behavior, and through that associate to each of them or to each typology some capacity curves, which we can then, through the N2 method, interacting them with natural or non-natural or synthetic spectra or compounded spectra, obtain fragility functions, which we can then use together with the exposure characterization to define risk and risk reduction measures. So this is where the FaMIVE basically, is set into. So now, if we start from the urban dimension, here you can see two very different cities, which are both highly characterized by masonry constructions. The L'Aquila city in Italy, which was affected by an earthquake in 2009, and the Lalitpur city in Nepal, in the Kathmandu Valley, also affected by a very strong earthquake in 2015. Both of these cities were subjected to substantial damage. L'Aquila more than Lalitpur, because Lalitpur was farther afield from the earthquake. But as we look at the view from the sky, we can see that both cities are characterized by a very dense pattern, but also a rather irregular pattern that has organically grown through the ages, and both are very historic locations. Can we identify through this pattern commonality, not just within a particular urban area, but across different urban areas? And can we extract from this the fundamental behavior of these structures so that we can then define their response to earthquakes, and we can therefore determine their vulnerability in an engineering, following an engineering approach. If we go down to the street, we can see that that difference and that variety is emphasized even more as a result, as I said, of this organic growth through the ages. And while we can really recognize some recurring element across the different urban streets, we can also clearly identify the substantial difference in typology across the two different elements. And we can also identify the fact that they are very irregular buildings. So how do we actually determine that? So let's then go down to the individual building. When in the occasion of the earthquake in L'Aquila, we did a very extensive level of survey of a large number of buildings that had been damaged, and we could clearly identify very different patterns of damage, what we call crack patterns, in buildings that, let's say, are not completely collapsed, and therefore we could start recognizing the type of mechanism that would eventually lead to collapse. In this case, we can see here out-of-plane mechanism, corner mechanisms, and the top so-called arch mechanisms in these three cases. If we go further in the observation, we can look more in detail at the in-plane failures. And in this case, we can recognize, oops, why it keeps jumping? I don't understand. We can recognize here quite, let's say, canonical pattern of X cracks that often is referred to when thinking about masonry failing in plane. But we can also see a less possibly considered pattern, but that is also the documented pattern, which is at the same time very common, of one single large shear cracks running across both piers and spandrels and running across the different stories in the building. When the structures are better connected at the top of the walls, when the facade are better connected, we can see that they actually fail in a different way again. And here we can see that this facade, which was well connected to the back and to the roof, so much so that the roof failed mid-span here, actually is bringing with it in its out-of-plane behavior also part of the side walls, also part of the in-plane walls. And therefore, we can represent with this type of sketch. And finally, here where the roof is consistent and provide a restraint towards the back, then we have what we call a arch type mechanism. You can see that the center level of the facade is here swaying out, and therefore we can identify this type of mechanisms. So how can we summarize these observations in a way that then take us to an actual structural model? I think the sketches by Professor Touliatos are very useful in this space, in this respect, because we can easily see that from an isolated wall, which will overturn, basically working in engineering term as an isolated cantilever, if we start connecting that same wall with the side walls and well connected, as you can see here, with coin stones, what are large stones that connect orthogonal walls, then the wall will not be able to deflect out as we saw before, and basically we will have the formation of a arch or beam behavior in this direction, where we will have maybe some crack towards the centers, but at the same time, the connection with the transversal wall will be will then transfer the forces generated by the inertia and the accelerations through the party walls, where we will get shear failures. And finally, if we can define a type of roof or horizontal structures that is sufficiently stiff in its plane, so that what we typically call a rigid diaphragm, then in this case, the top of the walls will also not be able to deflect and move out, which means that we will have, as you can see, an effect of double bending, and therefore an effect of further reductions of deformation and greater stiffness, but also greater strength as the forces are redistributed through the whole four walls. So with that in mind, then, if we want to summarize from the perspective of Professor Hendry, since 1997, the behavior of a full buildings in engineering term, we can clearly see that the facade that is, let's say, impacted by the acceleration will tend to bend in one or two directions. This might be restrained by the slab at the top and the slab at the bottom, and will transfer the load to the cross walls or to the side walls. This is all fine and well, and indeed the roof, as you can see in this particular picture here, can be quite stiff and rigid, but if it's not appropriately connected to the facade, and if the facade doesn't have a level of internal connection to the masonry and to the party wall, this is how we end up. The roof is still in place, but the facade might have collapsed. So it's not sufficient to think about a rigid wall or a rigid roof, but we need to think about the relative stiffness of all the parts and how they can work together without concentrating failures at particular point. So at this point, it's very important to identify the typology and the specific element of the constructions that determine the different behavior, as we said earlier. So we can have In doing so, we need to pay attention to the horizontal structures. Are these timber floors? Are these walls? Are these concrete slabs, for instance? At the distribution of the opening layout, at the materials that constitute the masonry, and as you can see, we can have very different fabrics, at construction features such as the points that we mentioned earlier, and how these construction features determine the wall connection. So in this case, for instance, we even have buttresses here that keep the walls together. And as you can see, for the time being, this is all observational. And then if we move somewhere else, this is Algiers, the Kasbah of Algiers in Algeria. We will have completely different features, but they also will substantially influence the behavior of these particular structures, and we will still have the need to characterize them in such a way that we can treat them from an engineering point of view. So this is the reason why we are developed this new FaMIVE shell, so that when the observation on site is facilitated and the collection of data is facilitated in such a way that then the data can be sent to us, and we can support you in analyzing such data. I hope that many of you, depending on the on your interest, have already downloaded the shell and have already started maybe playing with it. There will be opportunity to discuss this further. Here you also have some literature that you can use. So you can see here that there are various tabs, and this will be further explained by Professor Guardiola, but I will quickly go through them to show you how from the sites we can use this information. So, as I said, we start at the urban level by looking at the way that the building is set in the urban fabric. And this is very important because the buildings in historic city center, typically buildings are not isolated, are connected to other buildings. They might share party wall, they might share side walls, or they might have different height and different stiffness with floor at different level, which, for instance, will induce hammering. This will also give us the opportunity to identify the number of facades that are indeed visible from the street, and therefore that you can easily survey, and that and their geolocation gives also a way of categorizing them and naming them using the name, for instance, of the block, and then the number of the building, and then the orientation of the facade, so that there is a unique record for that particular facade. The next bit is to understand, of course, the number of floors, the total height and the total length of the facade, and clearly there will be situation where the number of floors is variable, so we need to think of how we are going to simulate that and how we can simplify this, still making it meaningful. So if we take, for instance, this particular sample in the city of Norcia, we can then see that we can start collecting the geometric data of the facade dimensions from the total length to the total height, which I previously mentioned. We are also very often buildings have a different height of first floor with respect to the other floors. So this is also an important element of information because, of course, they have a longer length of inflections than the upper stories. We are very interested in the dimensions in height and width of the opening, because this will then determine the piers. And we are also interested in the heights of the spandrel. Once this information is obtained, we then are interested in understanding the alignment of the windows. In this case, these are quite the openings. They are quite regularly aligned, even though, as you can see, they have different size. And how that alignment is categorized with different codes, which will be further explained later, and that can be assigned story by story. And the alignment will then determine the relationship between the opening and the side piers, and whether the piers are regular or non-regular, i.e. wider or narrower than the opening closer to the edge. And this is, again, quite important because it will determine that those lateral cracks that we have seen occurring earlier. The next element of information, as I said earlier, we need to define the horizontal structures and the roof structures, and we also need to define the way in which the structures are laid out, i.e. if they are laid orthogonal to the facade and therefore they actually load the facade, or if they are parallel to the facade and therefore their load goes onto the party walls mainly, or if they are concrete slabs, they will share their load, onto both set of walls. So again, once you have identified this, and this might require access within the building or might require a knowledge of how typical certain construction characteristics are within the urban area that you are considering, then you will be able to categorize here the different typology. And once you provide that category, then FaMIVE directly assigns value for the gravity loads and the of both floors and roof structures, and in both on both sets of walls. Naturally, you might be these are for unit of area. But indeed, you might have knowledge that in your particular structures are different level of loading, and FaMIVE is also designed in such a way that these values can be easily altered, but also that other typologies can be added if you identify one, and we can therefore tailor the procedure to suit your model or your typologies. So here, for instance, we have, oops, sorry. But why keep jumping? Oops. Okay. What is also important in the determination of the loads that are related to each set of walls and to the facade is, of course, the total length of the building perpendicular to the facade, so the plot, and the number of internal walls that divide that plot, so that we can understand what portion of the surface area goes onto each of the walls. The next step is to identify the masonry characteristics and the thickness of the walls, because again, we need to determine the mass. So we can easily see the thickness at the bottom, usually from open entrances. It might be more difficult to determine the thickness at the top unless we can enter the building. But again, it can be done through looking through a particular opening. Very importantly, we need to define the dimensions of the unit that constitute the masonry. And in this case, it's a very regular masonry, TAFA units, where we want to particularly know the length of the unit, the height of the unit, and they're overlapping, they're staggering, because as you might already be aware, cracks will form in this way, and we want to be able to describe that cracking. Now, there are many different types of masonry fabrics, from more regular squared or worked stones to brickwork, to irregular worked hewed stones, to rubble and mixed maybe with brickwork, to adobe or hollow brickworks and so on, and or multi-leaves walls. Again, we have considered many of them in various different way. You can categorize yours following these descriptions. If you have a different type of masonry fabric, again, you can illustrate it, and then we can add it as a new input. And by doing that, we can easily define then the dimensions of the units, as we have already determined, the type of connections within the wall, within the thickness, and therefore within the wall, if the level of connection in the thickness is sufficient to guarantee that the wall is integral, and if the level of cohesion of the fabric is sufficient to determine a certain cohesion. To each particular typology, we also associate a specific weight and a friction coefficient, which we take from a library and from past test exercise. But again, if you have specific value that you have determined with, for instance, experimental test, then that can also be accommodated. It keeps jumping. I'm very sorry about this. Eccoci. So, what's wrong with it? I mentioned earlier that we want to define a box behavior, and I'm looking at this particular example here because we can see that this particular building has all the elements that support and enhance the collaboration of walls working together. We can start from the ties or anchors, as that you can see here, but also along the wall here, which tie together the wall to internal walls, party walls, but also in this case to floor elements here, and to party walls possibly above here. Then we can see what we call the points, reinforced, very carefully hewed stones that ensures a good connections between the orthogonal walls, as opposed to a continuous break in between them. And then we can also see here that we have buttresses. So FaMIVE, it's able to account for all of this, and you can define what is the presence of these elements at each of the stories, 1 to 5, and for each of type of these elements, including timber bands, ring beams that we can see here at the top. So although this building looks very traditional and historic, indeed, this can be quite easily recognized as a latter intervention, possibly in the mid to late 20th century, where a concrete ring beam had been introduced at the top here. You might argue that yes, that this building is still damaged. That's true. We can see that the masonry fabric of the building is quite irregular and looks quite rubbly. There are several cracks, but the building is still standing. So clearly these elements have contributed to its survival vis-a-vis many other buildings in the area that are collapsed. And talking of connection between walls and how we can recognize them, again, here you can see very clearly for instance, that there is these junctions between these two buildings, and that the building on the left has no connections, the facade has no connections to the party wall of the building on the right, while here there are clearly return stones that connect into it. This side is held with some ties. Here it's held again with some cornerstones, the same cornerstones we see on the left, and the photos on the extreme left of your video is the side vision of this particular building. Again, with ties which do not have a very regular distribution, and that's why we proceeds to give you the possibility of entering the presence of ties at each different floors, and whether they are along one particular alignment or different alignment. And again, here we can see a crack, which is concerning, but again, the building, as notwithstanding being again of a very roughly hewn masonry and very old, possibly 200 or 300 years old, has not collapsed. Why are ties important? Ties are important because they prevent the walls overturning, so they will not prevent the cracking, as we can see here, and as we can see here in reality, but they will keep the walls together, and therefore they will prevent catastrophic damage and collapse. So, what is the effect of all of this at urban level, where we started from? So we did an analysis of the constructions, characteristic and fabric in the two cities of Norcia and Amatrice, which have been affected by the earthquake in 2016 in central Italy. And we can see here some differences. So, for instance, in terms of the quality of the masonry, which was clearly much better in Norcia than in Amatrice. We can see here that the horizontal structures were, to a certain extent, similar in terms of wood floor and vaults, but there was a high proportion of concrete floors in Amatrice. We can see here that there were many concrete slab also in terms of roof in Amatrice, but also, again, very importantly, no buttresses in Amatrice, but a large number of ring beam. And indeed, the results between the two effect of the earthquakes in Amatrice and in Norcia is clearly visible, both from aerial satellites view and from the street view, where we can see the almost total destructions of the historic town center of Amatrice on the left, and the survival with some isolated damage of the larger buildings in Norcia. So this is perhaps a good time to pass the mic to Professor Arianna Guardiola-Villora, which will present the way in which the data can be collected. In the meantime, if you have questions, please put them in the question and answer, and I will try to answer them to the best of my knowledge. I will stop share now so that Arianna pass the microphone to you.
Thank you, Dina. Hello, everyone. And my screen?
Not in the presentation mode yet.
Okay. Presentation. Now? Can you see my screen?
Yes, now it's perfect.
Well, yes, but I'm also Okay. Thank you. Well, I'm Mariana Guardiola. I'm going to present how to use FaMIVE shell. And for that purpose, I will present the following points. First, how to download and install FaMIVE shell. Then I will show you a general overview with some of the examples included in the database that is installed when you install FaMIVE shell. After that, I will show how to use the shell with a new example from scratch. And I will send at the end of this example the data to the UNESCO chair to be analyzed. And in the meantime, I will propose you some exercises. Probably you have the document with them. And then I will finish giving the floor to Professor Dayala, that she will show you the results of the example of application. Okay, you can download the FaMIVE shell from the Epicenter webpage. Here you have the link at UCL. You have the menu Epicenter resources. Here is FaMIVE. You will direct it to this link to download the shell. And this is directed to a Dropbox folder with two files, the setup and the README PDF. Because Microsoft Defender may block the downloading, first you have to download the README PDF, and then following the instructions, you download the FaMIVE shell setup. And to install it, you have just to click on the setup. And after that, the following folders and files will be copied in your computer. The folder databases with one example of a database with different facades is a text file. And some of the facades have pictures that are stored in this folder example pictures. The folder environment includes a .NET routine that you need to run the shell. Maybe you have this one installed because most of the apps need this routine. If when you are trying to install it, you need to install the net, you know that is here. Oh, what happened? Sorry. And then you have the folder manual with document where the approach, FaMIVE approach is explained at the beginning, and then how to use the shell. To run the shell, just click on FaMIVE shell exe. And if you want to uninstall, I wish you don't, then you have here an installer. Okay, the second point is to show you how the shell works. So I'm going to exit the presentation and I'm going to start the shell. So here's the shell. The shell has been designed with different tabs and different buttons here on the right. The tabs are organized to be fill the data in this direction, but you can go back if you want to change some of the data. With the buttons, you can result of values. If you want to start from scratch, we will see it in the following example, or send the data that you have introduced to the clipboard, to a database, or to an Excel file. You can send the data to a database with this button, and then you can load this database. I'm going to load the database that is included with the installation, but I've got one copy in my desktop because I'm going to change some of the values. And when I try to save the changes in the folder where it's installed FaMIVE shell, in this case is program files, I don't have the permission to write in that folder. So I've got one copy in my desktop just to play today with it. When I choose one folder, one ID, I have one summary of the main data of this facade. And then here I've got all the fields corresponding to that facade field. In this case, I don't have a picture store of this facade, so I have one drawing here, but if I choose a different one, and in the corresponding folder is one picture with the same name of the ID of the facade, this list are the IDs, then I can see the picture of my facade. And you can see that more or less the layout of the openings is similar. Those are all the facades that are included in the database that is copied in your computer when you install the shell. Just if you want to check how it works, you can load or unload. It's important to point out that you cannot have two facades with the same ID in the same database. If this is the one I'm working with, here is the ID. I will show you how this is formed. If I try to save this data to the same data file, do you want to send this in this ID in this file example, that is the one I've opened, and I say yes, then I've got a warning that I have one with the same ID. So I can overwrite it, or if I say no, then I'm not saving the data. Of course, I can save this to not the same database, not this one, a new one that I'm going to create now. Testing. Okay, so now I have one new database. I can load it, test it, and this is the one I have just created with just one facade. More things. Okay, in the database, we have some help, 3 different ways to access to the help. One is when you hover in one of the drop menus, if your mouse is near it, you have this pop-up window with the explanation for each of the options. If the text that we need to explain the different options is longer, then we have this question mark button, and a new window opens with the explanation of the different cases. This is the second one. The third help that we have is based on drawings to explain some of the values or the data that must be filled in some of the fields. I'm here in this tab that is facade, and one of the fields is number of stories of the building. So here I've got one drawing explaining the number of story of the building or the number of stories of the facade. It can be different. If I'm go with my mouse near additional corner, here I've got one drawing with the explanation of the additional corner meaning. If I go near gable, what is expected to introduce in the data regarding the gable, the dimension of the piers. We have just seen that we have 3 different types, regular, or the ones that are smaller than the width of the openings, or the ones that are bigger, or the layout, how the openings are organized in the facade. Okay, this is the second point. Now I'm going to go along the different tabs, because we have some limits for some values and some values, some data that are compulsory. For example, the name of the surveyor is one of those compulsory values. If I try to go ahead to the following tab, I have this warning that the name of the surveyor must be specified, and at last 2 letters are required. So I can go changing different tabs, but in any case, before the end of this facade, I should provide my name at least with 2 letters. It's also compulsory the type of soil. We have 3 types of soil. And In each of the tabs, we have the field reliability of the data. It's in each case related with the data of this tab. This is important. All the fields regarding the reliability at each tab must be filled, because this sets how accurate are our data. And this is linked totally with the source of our data. So here we have high if the data have been collected on site and measured with an accurate tool. I would say in this case they are high, their reliability. If we have been on site, but some of the values were not able to be measured because it was not possible to access, or because we just estimate the value, then we will choose a reliability medium, and low when we have the data collected from pictures or from Google Street and so on. So the accuracy of the data is lower. And this is important because the results are totally connected with the reliability, and the boundaries of the results depend on the reliability of each data. So we have compulsory fields. We have limits. I cannot have more than 5 stories. So if I try to input 6, then I've got a warning. Okay, it's not 6, so I've got 5. If I change the value of the maximum number of stories, then the maximum number of stories of the facade must change. So those are the sensible values, and we will find these values in all the tabs. In openings, for example, the length of the lintels should be bigger or equal than the width of the wider opening at each level. In the structure, sorry, in the layout, the thickness at the top of the facade should be equal or smaller than the thickness at the basis of the facade. If I try to input a bigger number, then I've got this warning message, okay, and is insert the sensible value 0.36 or a smaller one. In the structure is where we choose the horizontal structure, the typology. Here we have the different typologies we've been in the previous presentation. And we have also to set the direction of this structure. If it's the load is bearing on the facade, so it's orthogonal, is parallel, or is OP, which is part of the load goes to the facade and part to the party walls. Regarding the type of masonry, here we have the different typologies. And as you can see, we have, for example, B1, B2, B3. All the 3 are brickwork, but with different quality. Good quality for B1, medium quality for B2, and poor quality for B3. So we try to link, if we choose B1, which is a good quality masonry, we have this suggestion regarding the level of connection across the wall thickness. So because I choose a good quality, suggest to set the connection high, but I can't change this value. This is a suggestion, but it's not compulsory. There are some elements that we can choose if we have them or not. For example, buttresses, we can choose no. If they exist, then we have to input the data. So if there are external buttresses, I have to click the box, and then I have an additional menu where I have to introduce the characteristics of the buttresses. And here is in the drawing the explanation. Then we have the tab vulnerability. This tab includes all the elements that increase the vulnerability of the building because are the ones that collapse first. Here we have the presence of vertical addition or parapet. Here we have the drawing. This part is the vertical addition. And once we choose that we have vertical addition, then we have the boxes to introduce the values. We have the possibility to introduce jetty wall, oriel windows, or balconies. And here's the drawing with the explanation for each one of these elements. We have the roof overhanging. And also in this tab is included the porticos. If we have porticos, you know that then it's probably that we have the soft story mechanism. If we have finished, if our facade is an undamaged facade, then we have finished with this tab, vulnerability, and the next tab will be submission. Submission, I will show you how to use this in the next example. Build the email with the data that we have to send to the UNESCO chair to be analyzed our facades. If our facade is a damaged facade, so I'm going to load the example database. Here we have some examples from L'Aquila. In this case, this facade, in the tab Damage and Mechanisms, we have additional data. Here we have the question mark, where we can see the different failure mechanisms, the ones that we are going to choose in these menus, and this question mark regarding the level of damage. If you choose B2, for instance, that is no, if you choose one of the mechanisms, partial B2, then it's compulsory to fill the damage grade. So, great. If the facade is a damaged facade, the data, to save the data, we have these buttons that are inside this tab. Those are the general buttons for the facades that are undamaged. But because we have additional data in the damaged facades, we have additional buttons to send also the data regarding the damage of the facade. And with this, we have finished the second point, how to more or less use the FaMIVE shell. And I'm going to explain from the beginning how to use it with a new example of application. In this case, this is my facade. I've got some data from the cadastral database, the number of the block and the building, the urban layout. I have some pictures from the on-site survey, not only regarding the layout of the openings, but also the structural characteristics. I've got the measure of the thickness of the wall. I can see that it's made with bricks. I can see also the horizontal structure. And I have also the original drawings from the historical archive. So with these original drawings, I've drawn the facade with the dimension of the openings to be introduced in the FaMIVE shell. Because the building is not a regular, it has not a regular plot, we are going to consider only this part of the building. Like if this bearing wall is back facade, and this distance is the one that I am going to consider to translate the load that is in this structural horizontal structure to the facade. Because as we saw in previous picture, the direction of the flow is orthogonal to the facade. Okay, once more. Out of the presentation. So here am I again in FaMIVE shell? And because I'm going to start from the beginning, and I don't want to have any mistake regarding the previous data from previous facades, I'm going to reset all values. This means that all values are set to 0, and maybe some of the values that now are not filled, for instance, the soil foundation, are compulsory values. So I have to take care of all the fields before sending the facade to a database or sending it to the UNESCO chair. I have to check that all the compulsory fields have been filled. Okay, this building is in Valencia. I'm from UPV. I'm Arianna. The address is Sorny 11. The main use is residential, but because we have this shop at the ground floor level, I could say that is 80%. And today is 9th of May, 2024. The number of the block is 64254. Have you seen how the ID is being formed with the, I forgot to say it before, with the number of the block, the number of the building. If I add some comment, just seminar, and in the middle, okay, the orientation of the facade. This is south facade. So here we have the ID. The access is good. The building is undamaged. The shape of the block is full diachronic. It grows in different times. We have 28 buildings in this block. The soil is loose, so it's number 3. And in this case, the reliability is high. I know all this data. The position of the building in this drawing is one of those in green, so it's immediate building S. And the connection of the facade to the adjacent walls, this is this black facade, no free corner, is the first option. We go to the second tab. The facade is an external facade with 5. Have you seen? I don't have any box here for the openings. When I choose the number of stories and the number of the stories at the facade, I've got then the boxes where I can input the dimensions of the openings. The length of the facade in meters, 16.1, and 21 the height of the facade. The ground floor is 6, and the average height of spandrels is 1. Because all this data comes from the original drawing, I will say that the reliability is high in this case too. Let's go back to the drawings. So we have 4 openings at each level. And we can see that we have 3 with the same dimensions, a different one at the top story. And then we have all these with the same width but different height, and the same in these 3 stories. And again, in the ground floor, we have 3 with the same dimensions and 1 that is different. So I'm going to fill the data in the quickest way. So I have 4 at each level. It's important to know that when I change one of the values, until I don't change the focus of the mouse, it's not an enter action. So when I input 4, but I have to click in a different box to enter this value. So here and here. It's important to take into account that the dimensions are in centimeters. All the other dimensions in the shell are in meters, but the dimension of the openings are in centimeters. In this case, there were 3 of them, 90 per 90. With this bottom, I can fill all the width and all the height for all the openings. And then I will change this one, which was 130 and 230. And this is the procedure I'm going to follow to fill the dimension of all the openings in the facade. So these were 130 and 240, 2 of them, but 2 of them were 290 and 290, if I remember, yes, 290. Then 130, fill width, fill height. This is the one that is 90 and 90. 240. In this case, I think this one is different. Is 265, 315. And this one is 315, 315, 270, 430. And this one is big, I think. I think this is 270, 360. Let's check to the original drawing. Yes, 270, okay. I've got the dimension of the openings, then I have to set the dimension of the piers. And we can see that here the distance is bigger than the width of the opening, the same on the right. I would say that on the left, in these 3 stories, is a regular pier. And on the right, is the dimension is bigger than the width of the opening. So I would say this is n minus and n plus, and n minus for the ground floor at both edges of the facade. So this is n plus, bigger than the width of the openings, regular on the left, n plus on the right, and in the ground floor, n minus and n minus. And then I have to set the layout. The layout, we have the drawing on the left, and we have the tooltip here. I would say is E to C openings with vertical alignment at both edges, and also a central column of openings. But we can just try one of the codes and transfer data to the following tab just to check. So transfer preliminary type of layout, openings, and so on. And then we can check here if the layout is more or less than the layout of our facade, which I would say it is. Let's check if we have all data here. We have the reliability. Okay, let's go for the following tab. In this tab, we see if the layout is what we are looking for. And we have to introduce the data regarding the prevalent lintels. We have a flat arch, beam, or arch as typologies, and the materials stone, bricks, timber, or concrete. If we go to the picture, we can see that we have flat arches. It seems that we don't have those flat arches in the ground floor, but here in the picture, we can see that we have them. So I'm going to select flat arch for all the lintels. In all the flat arch, in all the cases are brick arcs, so it's B. And then the length, as I said before, should be bigger, longer than the width of the wider opening at each level. So in this case, we have here the width, 130 centimeters, the length at least 1.3 meters. If I try to introduce a smaller value, then I have this warning that it should be at least 1.3, okay? And it changes the value. 1.3, and this one is 2.7. And I could say also in this case, because we have the original drawings, that is high the reliability. I validate the change and go to the next tab. In the next tab, I have to introduce the information regarding the thickness of the facade, but also here the layout with the orthogonal or parallel bearing walls. We saw that we don't have any. And this distance. So go back here. The thickness, because I've measured it, but you can see also here, it's the thickness is 2.5 bricks. So this is standard brick is 0.24. So it's equivalent to 0.6 meters. I know this data, but not this one. So I estimate that it's going to be 1.48, equivalent to 2 bricks. But in this case, the reliability is going to be medium because I don't know this value for sure. I don't have structural walls orthogonal or parallel to the facade. This length is 5.5, and I don't have any bearing wall orthogonal to the back facade. So imagine that you don't have to fill all the data of the facade in one time. You can have one break. But I'm going to save those data because I've done some work, sending them to a database file. And because I have not finished the facade, I have some compulsory fields that must be input, and I have not. I know the type of orientation has not been specified, I know. And so I have one warning. Do you want to proceed anyway? You have not finished the facade, but yes, I need a break, yes. So do you want to send the data? And we have here incomplete, just to advise us that we are sending data for an incomplete facade. So it's offering to save them in the same database I used before. I want to create a new one. No. Yes, I want to send it to a new one that is seminar. Save. So the data of this ID with incomplete included and be sent there. And here we have this comment that the facade is not complete. I have to remove it at the end when everything is filled. So I have to remember it. I was here. I can just continue filling the same values, the different values in the different tabs, or load the database. Is the same. Let's go for the horizontal structure. The roof, I would say that is A2 timber joist with screed. I'm not sure about this because I haven't seen the roof, but I would say that the direction is the same as the direction in the other floors. We've seen the structure that floor 1, which is a A3, timber joist with planks, orthogonal to the facade. And I will select the same typology for all the stories. but because I'm not sure 100% of all the data, the reliability, I'm going to set it like medium. We don't have restraining elements like anchors. Here we have the drawing regarding of each of these restraining elements, coins, timber bands, or concrete twins. The masonry type, I would say that is B1, good quality of bricks. So as I showed before, the level of connection has been set. I do agree with this level of connection. The masonry mortar is lime. The level of maintenance, I could say that is high. We have the options low, medium, high, or not updated. So it's high. The level of water infiltration is low, and low level of mortar loss. Standard bricks, the length 0.24, 0.06 the height, and the overlap has been set as 1/2 of the length, but I can change this value. It's just a suggestion. And also assume that it's well connected at both edges, and we don't have external buttresses on anything else. So let's go to the last tab, because it's an undamaged facade vulnerability. Go back to the drawings. We have this vertical addition. Because it's not a regular rectangle, I've set the height in 0.85, just assuming that this area is the area that I'm missing there. So the load corresponding to this vertical addition is going to be equivalent. So I've got vertical addition, one floor. The length is 6 meters, 0.85 the height, and I don't know the thickness. I assume that is one brick, the structure of the brick, so 0.24. We also have balconies, but in our facade, we have 2 different balconies at each floor, in these 3 floors. I'm going to add this length to that length, 3.10 plus 3.10, as the total length of balconies at each level. So I have balconies in 3 stories. The depth is 0.85. Here is the meaning of the depth. The length, I said, is 6.2. And the thickness, here, the thickness of the slab, 0.25. We also have roof overhanging. You can see it from the pictures. Here, I cannot measure it. I was there and I estimated it in 0.60 or 65 meters. And we have struts, 4, 3, 3, and 4. So we have 0.65 and 14 struts. We don't have porticos, no chimney, and the reliability medium. With this, I finish the facade. If I send the data to a database file, the same I was using, is one file with the name incomplete. I would say yes, I want to overwrite it, but it's not incomplete, it is finished. So I can just add the word finish, or you can save the incomplete facades in one database with all the uncompleted, and then the facades that are finished, sending in a different database just to send them to the UNESCO chair. So this one is finished. I'm going to send it to the same database, yes, and I'm going to load it just to see
Ariana, you're muted. Ariana, you're muted.
Okay, now?
Yes, now we can hear you.
Okay.
I think we lost you while you were saving.
I'm sorry. Okay, I'm going to go back. I had this facade that was incomplete. I'm going to, I don't want to see you, sorry. I'm going to send this to the database.
Can you see the thing? No, you are also not sharing the screen, it seems.
Okay.
For some reason.
I didn't touch anything. I just, okay, but I'm Zoom. I cannot come to the meeting. Share.
Yes. No? Why it's behaving?
Can you hear me and see my screen?
We can hear you, but we cannot see your screen.
I don't know why. Share my screen. Share. I'm sharing now.
Yes, now we can see it.
Don't send.
We can see it now.
Okay, and can you hear me?
Yes.
Yes, perfect. So I was here.
Yes.
Well, I have the incomplete facade, the one I saved in the meantime. And after that, I finished all the elements. I filled all the fields. So I send this facade to the database, removing the word incomplete. So I'm going to send this to the same database, the one named seminar. Yes. And if I load this database, I have the incomplete, the one that is named seminar, and the one that I finished before I went out of the seminar. I don't know why, when Zoom decided not to share my screen. So I'm going to delete all the facades that I don't need, for sure the incomplete. Be careful because this cannot be undone. So if you delete forever and ever, okay? This one and that one. Okay, so this is the last one I have that is finished. I'm going to check that I've got all the fields filled. Also the reliability, structure and vulnerability. And then I go to submission tab, where I've got the data of this facade. This is the text that has to be sent, the email. I need to fill my data, Ariana Guardiola. And if you see here, is this in the body of the mail with my data is filling the data in the email from Spain, and the facades are in this case in Valencia. All this data with this button are sent to the clipboard. So then I go to the email, I paste this data. Here I've got the UNESCO email for FaMIVE. the subject of this email, request for seismic vulnerability analysis, I can remove this text. And I have to attach, although the data are included in the body of the mail, I have to attach also the database. Desktop, it was seminar. So I'm going to send this email with my facade to be analyzed. And with this, we have finished the third point, how to use the database. And in the meantime, we want to propose you 3 different examples to use the shell. And you probably have this document. We sent it to you. And I think the best way to understand how to use one app is just using it. And here you have the SKUs. You can fill the data for one facade, 2, or all the 3. And you have to decide the reliability of the data, considering that in the first example, the data were obtained in a field trip, observation from the street without accessing the building. In the second case, the data were obtained from pictures and the cadastral database. But the cadastral database gave us some accurate dimensions. And the third case, the data were obtained for the original project, a field trip, and the cadastral database. So with these examples, we suggest you to try to download the shell and try to use it with these examples. You can set the database. This is, if you input the data for all the 3, I've done it. So I upload is the proposed exercises. I've got the results. And here are the different facades. I've got the pictures too. You have the pictures because they are in the document. You don't have to send the pictures, just the string, the data. So you have to send all the 3 facades in the same database, or just one, depending on what you've done and your interest, to the UNESCO chair, and you will have some feedback as soon as possible. And at this point, I'm going to give pass to Professor Ayala. She will explain the results of the analysis of the facade I sent. And if you have any question about FaMIVE shell or any problems, you can contact me by email at any moment, not just today or tomorrow. I will be grateful to try to understand your problems and to solve your issues. Thank you. And now, Dina.
Thank you very much.
The floor is yours.
Thank you very much, Arianna. I don't know if you can see my screen.
No.
What about now? So, yes. Is it coming? Yes, thank you. So again, Arianna, thank you very much for explaining in great detail how to use the shell. I think there might be some questions for you waiting in the question and answer sessions. So just to say that please try to use the shell and send us your input, and we will run it overnight, and then tomorrow afternoon we will be able to discuss further the results and what do they mean. In the meantime, Arianna sent me a model facade earlier, the one that I just filled in with all of you. So we want to see which mechanisms will develop. So how does the FaMIVE works from an analytical point of view? These are the mechanisms that we have already identified earlier from the street. For each of them, if I manage to change slide. Sorry. If this, I don't know why it gets blocked. Yes, for each of them, as you can see here, so for mechanism A, for instance, it's a simple overturning of just the facade. We have an equations that computes what we call the collapse load factor. These equations relate basically the overturning moment with the stabilizing moment for each of these conditions. And so using limit state analysis, basically what we do, we predetermine a mechanisms for the facade, and then we compute all possible solutions depending on the number of stories that are involved in that particular mechanisms. These equations are then included in an algorithm and programmed in Visual Basics and Excel so that we obtain the results. And for each of the mechanisms, we consider the minimum case. So here, for instance, we can recognize some of the inputs that you are requested. T stands for thickness, L stands for the length of the facade, AH is the height of the stories, or and therefore, and beta is the number of internal bearing walls orthogonal to the facade, which effectively restrain the facade from overturning. Mu here appears as the friction coefficient, which together with the size and the staggering and length of the brick will allow us to determine the friction effect that will help restraining the wall from overturning. And these are the loads that are transferred to the facade with the walls, with the floors and stories. So the relationship here between the restoring moment and the overturning moment will give us the eventual collapse load factor. So this one is slightly modified if we consider only half of the facade, because a crack will occur diagonally instead of vertically. It will again be modified by the fact that only part of the facade might fail instead of the whole facade, depending on the layout of the window. Again, when we go into the combined mechanisms, it's a similar principles, but we are looking at also involving part of the side walls, only one in mechanism B1 or both of them in mechanism B2 in a more symmetrical fashions. We can consider also the overturning of the corner if there is a strong point, but the masonry is weak within the facades. And each of these, as I said earlier, will be optimized and minimized according to the critical parameters that we need to include. Here, for instance, the angle alpha help us to define which portion of the side walls will come in, and here similarly how this will develop in the diagonal fashion. As far as the in-plane mechanisms are concerned, again, we have two different possibilities for the X-cracks. So we consider whether they will occur in line with the just in pure frictions, or also associated with the staggering of the brickworks, and therefore along a particular line of cracking, where alpha P and alpha B are the differences between the angle of the shape ratio of the panel or the facade and the shape ratio of the brickwork, or as we saw earlier on, in a manner that identifies this singularity of crack which then requires a much more complex set of forces to be put in equilibrium together with the friction resistance that goes along the crack itself. And again, you know, we consider that the crack might occur only at the top floor, or might occur over 2 floors, or might occur over 3 or 4 or the whole 5 floors. Is the facade has 5 floors. And as you can see here, it can take different different paths depending on whether the depending on the alignment of the windows and whether the spandrels will be stronger than the piers given their geometric ratios and so on and so forth. So that's why we start understanding why so many of the parameters that we require in the input then become essential to the analysis. And again, just in case here, we have also carried out some discrete element analysis with 3DEC to validate this type of mechanism that we have developed here. Again, if we have the ties, the anchors, so if the top part of the facade is restrained from moving out and therefore can only rotate, we will have again a more complex type of mechanism which is described with these equations. With this here, one unknown is where exactly this crack will take place. It's at this level, it's at this level, it's at over 4 floors, for instance, will be higher up and so on. And so that also is optimized within the routine. And finally, we have the horizontal arch effect, which is very common in facades that are well restrained along the edges, but not at the top, and which produce, I don't know why this one jumps, which produce this type of failure. And again, this type of failure may occur. Here, the unknown is the diagonal line, which will depend both on the ratio of height to width, but also on the type of fabric. And again, the size of the brickwork and the masonry is very important, but it will also depend on the distribution of the loading conditions on the walls or on the side walls. So, and here, for instance, you can also notice that we use different level of thicknesses. So also the importance of determining the thickness between the top and the bottom becomes extremely relevant. To finish, we consider also a mechanism where you have portico, so where you have relatively slender elements at the bottom, which support a continuous facade at the top. This will produce a soft story mechanism. And we have a mechanism for the buttress where it's true that the buttress have a very good effect may have a very good effect on the masonry, but if they are not properly keyed into the original masonry, then they might detach independently, and therefore they might not be as effective as we would wish. So how does the FaMIVE algorithm work? So after the data collection with the shell, we do a number of checks with the storage and that the data is all consistent and correct. We then create a record. Then for each facade, we assign the gravity loads according to the horizontal and masonry structures and masonry typology that you've chosen, as we have seen earlier. We then also assign a friction coefficient and a level of cohesion, which will depend on the quality of the masonry that you have included. We will check the boundary conditions, if the connection at the edges are present. And then, depending on other elements, now we'll jump back. depending on other elements, so the presence of ties, for instance, will compute mechanism F. If there are porticos, we'll compute mechanism M1 and 2. If there are buttresses, we'll compute 2 types of mechanism relating to the buttresses. On the other end, if there are good connections, so we will look at the connection of the cross walls. If there are no good connection, then we assume that mechanism A, D, and E will occur. But if there are good connections, then we will assume that mechanism B1, B2, C, and G will occur instead. Or if there are a very heavy reinforced concrete ring beams, then we will also compute the information, the mass that is given by the ring beam, and then we will recompute all these elements to all the mechanism to determine for each facade. I don't know, but stop jumping, please. Yes. For each facade and for each story, the collapse load factor. This is called ESC. For each mechanisms, we will look also at what we call the damage index, which is the proportion of the facades that fails in that particular collapse, and whether that collapse occurs also with the floors, and therefore it's much more destructive, or without the floors. And out of these 2 parameters, so the damage index and the equivalent base share coefficient, we will then combine them to provide a vulnerability index. The mechanism for which the vulnerability index is maximum, then we consider the mechanism that will indeed, it's the most critical for that facade, and therefore we will output that particular mechanisms in our summary. That doesn't mean that the other mechanisms are not occurring. This means only that we are identified the one that has that provides the maximum vulnerability for the facade. So when you will receive the output of your results, these are the results for the particular facade that Arianna sent earlier. We can see here that we have different sets, which I will describe in the following slides more in details, but basically under mechanism H2, we can see here that we have the minimum value of the collapse load factor. This minimum value of the collapse load factor, we can come here and we can see that is also associated to the maximum value of the vulnerability index, although we can see in the other parts that there are very similar value. And therefore, this is, as I said, chosen as the final result or as the critical value. What I will also like you to note here is that for each of the mechanism, we have a central value, which is computed with the one that you have with the values that you have inputted. And then we have a lower bound and an upper bound that are determined using your reliability scoring. So we are assuming that each of the parameters that you have included have a certain variability, which will be wider or narrower depending on the level of reliability that you have scored, and therefore this range will be smaller or greater. Just to go a little bit more in details, so this is the family of out-of-plane mechanism we had already identified earlier, in particularly whether they have or they do not have good connections. So in this case, for instance, there were good connections in both at both edges of the facade. So as you can see, all the other mechanisms are not computed, only B2 is computed, and also E is computed because while the connections, the edges of the facade is good, the way that the windows are aligned and the way that the spandrel are connected to the pier might be such that the internal portion of the facade can also fail in this fashion. We then consider G again, because there is good connection on both edges. And then we consider the mechanism type A in plane, and we can see that the minimum comes from there. We will look at the partial mechanism. So in that case, there was a sober elevation of a portion of the facade, which has also produced one particular overturning, but there was no gable in that facade, so L is equal to 0. The soft story is not computed, the buttresses are not computed, and the ring beams are not the mechanism associated with the ring beams are not computed because we don't have the ring beams or buttresses or a soft story. In substance, you will also have an image of the facades that corresponds in a schematic way to your pictures. You will have the, as I said, the summary here for the final mechanism, which also tells you what is the level of vulnerability, and we will have the slenderness in the different portion of the facade, because the overturning and the failure is very strictly connected to the slenderness of the elements. And so here you have a very quick overview of different level of slenderness in the plane of the facade with respect to the thickness, with respect to the thickness to the height and the thickness to the width, and also of the individual pier slenderness and the corresponding level of collapse load factor that you get. So that all said, then we have determined the facade of individual, the vulnerability of an individual facades, but we want to go back to the building in its own right. So if we have all elevation of the building, we can consider all its elevation, we can analyze all the facade, we can extract the minimum collapse load factor for each facade, and then we can compare them to determine the overall minimum collapse load factor for the building. How we can use these informations, now we go towards the latter part of the presentation when we want to see how useful is the output from FaMIVE. So in this particular case, for instance, this is a case that we studied sometimes back in Slovenia, in the city of Ljubljana. There is a particular set of buildings set in crescent fashions. They were all built more or less at the same time. We collected the data on site as much as possible, and we can see that across, for some of them was either not possible collecting the data, or some of them had been changed into reinforced concrete structures, so there was no, they were not feasible for analysis with this particular model. So we looked at the way in which where the building behaved if there was no connection with party walls, in the case whether there were connections with party walls, and in the case in which there were effective anchors and ties. We can then consider the cumulative distribution of the collapse load factors in terms of the set that we have considered, and we can consider that cumulative distribution with respect, for instance, to the maximum expected base share corresponding to 72 years of return period and 475 years of return period for that particular site, and understanding which proportion of the building we can expect to be damaged and how effective would be having anchors on all of them, reducing, for instance, the expected percentage of damage building from 70% to 30%. Another way is to determine the collapse load factor, from the collapse load factor, the capacity curves, by using the characteristic of the facades that we had seen before, and particularly determining the, we have the mass from the information that you provided. We then need to determine the stiffness so that we can then determine a natural period. And by determining the effective stiffness and the effective mass, we can then determine, as I said, the natural periods. We can then define 4 points or 5 points capacity curves, multilinear capacity curves that allow us to, for instance, in this case, determine different capacity curves for different typology or for different type of failure by averaging among a number of facades. And as you can see here, again, we are using geometric information that you had inputted at the beginning, from the thickness to the effective height of the portion overturning to the staggering and so on. So this then, for instance, is what we would get for the city of Norcia, which I had introduced earlier, in terms of obtaining the capacity curves for each of the facades. And then from this, by considering the seismic hazards, whether in terms of, again, distributed expected PGA for a given return period, or whether using natural recorded spectra such as the one obtained from the 2016 earthquake, we can apply the N2 value, choosing the type of soil, for instance, and choosing the correct PGA with an elastic response spectrum, in this case, from the code, in order to determine the performance point by using the N2 method. And here I refer you to a previous course that you can access here, where we have in detail explained how this works. Now I don't have the time to do it. But we can then identify here the performance point in relation to the different damage thresholds and damage range. We can then correlate these damage thresholds. So the performance point is in the damage threshold of structural damage. And we can correlate that to a level of damage which is substantial to heavy, in a qualitative way, and in reference to the grade that you could have assigned on site, as we have seen before in the input part by Professor Arianna Guardiola. So once you have done that for a number of facades, then we can extract again for a number of input spectra. We can then use a typical way of deriving fragility curves with a log normal model, which will determine the median and standard deviation of the distribution of performance points. And you will use log normal regression models to define the fragility functions. And here you have two examples for different height, or still in relation to the Norcia sample, for different level of ductility according to the classification that is provided in GEM, and for different level of height between these two. And you can see that there is quite a bit of difference. when the different ductility is concerned. And with this, we are concluding this session today with 4 minutes to spare. If anybody wants to open their mic and ask any question, you are all welcome. Here you have a long, relatively comprehensive list of literature that you can refer to that will take you through the various level of development of the FaMIVE approach and model, and also through the to the latest applications. For the ones of you that might attend the World Conference of Earthquake Engineering, we will also have a number of papers presented there with the latest applications, which also corresponds to some of the talk that will be given tomorrow, where we will see more of this latter part of the exploitation of the FaMIVE procedures in determining the risk at territorial and urban level, and eventually also determining possible interventions at territorial level to improve the construction assets and the historic building and historic centers. With this, we thank you very much for your attention. I will stop to share, but as I said, if anybody wants to open up the mics and ask any question, you are very welcome. Thank you again for your attention, and send any questions that you might have to either myself or Professor Arianna. We will be happy to answer you. And so I don't know if there is any question there. Somebody's asking how the damage index is calculated. So you can look at some of the reference that I have in the line to look at it more in details. But basically, the damage index is a combination of the extent of the facade and the floor structures that have failed. So the quantity of materials that it's involved in the collapse and the periculosity of the collapse. So overturning collapse are considered have a higher weight than the in-plane collapse, because the in-plane failure are usually more stable. So you might see many cracks, but the wall will not overturn. And so we are using different weights to account for this. So we have another question. What kind of tools are used by you to analyze this data? Is there any procedure you recommend? Why is this not made by the software itself? Okay, so the procedures is separated in 2 parts. One part for the data collection and one part for the analysis. We have released at this particular moment in time the data collections. It's free of access. The portion that makes the analysis is not free to use, for the simple fact that it's, as I said, a rather flexible, open procedures and platform, which we tend to tailor to different use and to different type of urban and specific constructions, as you might have seen from some of the slides. If you are interested in using it, by all means, contact us, collect your data, or ask us advice on how you can collect your data. If there is anything specific that you would like us to take into account in the software, we can then update that, and then we will provide you with the results as I've shown in the slides. And also we will support you with the interpretation of the results. Okay, we have one more question from Rabindra Adhikari. Thank you very much, Rabindra, from your questions. I'm not sure what exactly you mean by I see the change in damage mechanism during earthquakes. Initial damage is one mechanism, and then the mechanism changed to other as the damage gradually increase. So if I interpret it well, yes, initially, depending on the level of shaking, you might have different type of cracking. So whether the mechanism changes completely, it's a different matter. You might have lighter cracking that you might interpret in a certain way, and then as the shaking increase, then but the increase of shaking usually will be due to aftershocks. So we have done some of the analysis considering aftershocks, which you can see in one of our papers by Dr. Putrino and myself, presented in 2019. If you would like to discuss these issues more, please, by all means, get in touch. And then we have another questions. Do you think this would work for not so regular dry masonry? Yes, this is one of the things that we are aiming to. So as you might have seen from some of the masonry typology that we propose, it can be just a rubble masonry with a very weak mortar. We make an assessment, and that's why it's so important, the level that you give an idea of the level of connections, both in the fabric of the walls, the level of staggering, which can be irregular or can be very modest, depending on the type of stones, and in the thickness of the wall as well. We will set an equivalent cohesion effect to account for this, and then we will put no cohesions if the masonry, if the mortar is very poor, and we will, and that's where we then take this into account. Of course, not to the level of detail of three-dimensional discrete element analysis, but we actually have validated some of the value that we use on the basis of such analysis, as I've shown, for instance, for one of the mechanisms. I hope that answers your question, Bernadette, but if that doesn't, please feel free to also come back and ask other questions. Louisa Bassett Salon, thank you for listening to us. And then there is a question by Fatima, whether we consider the age of the buildings in the software. We do in a way. So we consider the state of conservation of the building. And if you, maybe we didn't emphasize this enough within the seminar, but there are 3 different levels of conservations, and to each level of conservation corresponds an equivalent reduction in the effective thickness of the wall, because typically poor conservation will result in a loss of mortar and therefore in a loss of the contact between bricks and between their capacity of working as a solid wall. So this is one way in which we consider the age. And of course, we look at the stonework. There is another question on whether our future webinar about strengthening structures will be public. Yes, all our webinars are public, and we will be very happy for you to attend, and we will advertise it as soon as we bring it together. And also Bernadette is asking if there is no mortar at all. Again, then in that case, we don't use cohesion. We just use the friction coefficient among the brickwork, among bricks or stones or units. So another question from Rabindra. The parameters that we use for the, let's say, the constitutive material parameters that we use in the analysis are only the coefficient of friction and the cohesion. These are entirely, they can be entirely customized if you have proper experimental data, or we use data that is related to these typical types of masonry that we have identified in our typology. Why do we use only friction and cohesion? Because typically the failure pattern and the collapse slope patterns that we see are very rarely related to compression failure. They might be related to tensile failure, but the tensile failure can be, the tensile strength can be derived by the cohesion and friction. So that's why we use these two parameters only. Is this software works about huge domed buildings as well? I have a separate spreadsheet to deal with domes. I can send you, Fatima, a paper that I developed with another one of my PhD students on that. Yes, but we can use also the loading of the domes on the facades. Indeed, we have a version of this software of the FaMIVE that works also with domes. So maybe if you drop us an email, we can support you with that. And thank you all for listening and appreciating the presentation. And I hope that you will be with us tomorrow, because there will be much more on it and many different ways of using it. Thank you again.